Welcome to today's Trane Engineers Newsletter Live program. I'm Jeanne Harshaw, and today we're going to discuss variable air volume systems. Specifically, we're going to discuss how to optimize and electrify them. Now, VAV systems have been used in our industry for over 50 years because they're efficient. They use a variable speed fan and can use an air side economizer to reduce refrigeration energy. Systems can be designed to provide simultaneous heating and cooling, and they're flexible. Heating and cooling could come from a variety of different types of equipment, ranging from small packaged direct expansion rooftop units to large built-up chilled water air handling systems. Today, we'll start the program by briefly defining the system, and then next we'll look at how system performance can be improved through control optimization. After that, we'll explore how to electrify the various components in a VAV system to reduce emissions. And finally, we'll look at some recent technological advancements and a case study. Now, that's a lot to cover. So for today's topic, we have application engineers Greg DuChane, Mayra Reyes, and Eric Sturm. First, Eric will provide a brief system overview.
Let's start with a review of what a multiple zone VAV system is. First, there's typically a rooftop or air handling unit. Here, we have an air handling unit that includes a mixing box to mix outdoor air for ventilation and recirculated air. Then filters, sometimes a heating coil, a cooling coil, a variable speed supply fan, possibly a relief or return fan, and controls. Unit cooling could be direct expansion refrigeration, like in a rooftop or split system, or a VRF system with a refrigerant coil. A chilled water coil is used in hydronic applications. Now, heat could come from hot water or steam, a gas-fired heat exchanger, electric heater, or a heat pump coil. Now, conditioned air from the unit travels through a duct system to the thermal zones. Each zone has a VAV box with a damper to regulate the flow of supply air. VAV boxes may be equipped with reheat coils to temper the supply air for individual zones. Air leaves the VAV box, travels through flex duct to a diffuser, then into the zone. Air leaves the zone through a return air system, which could be an open plenum or a ducted return. VAV boxes are connected to zone temperature sensors. When the zone temperature has deviated from set point, the VAV box controller responds by adjusting the damper to provide more or less airflow. The central unit controller modulates cooling capacity to maintain discharge air temperature set point, for example, 55 degrees Fahrenheit. The controller also adjusts the supply fan speed to maintain a programmed static pressure set point. The static pressure can be measured from the longest duct run. As VAV boxes close and restrict airflow, the resulting duct static pressure increases, and the supply fan speed is reduced to maintain the set point. Next, a system controller may be used to choreograph system operation. Now, during times of part load, the VAV dampers close to restrict airflow, and the supply fan speed is slowed to deliver less airflow, which saves energy. This is one of the advantages of a VAV system, the ability to provide a variable volume of conditioned air. Systems of the past would use a constant volume of supply air. But VAV systems vary the airflow, which allows fan energy savings at part speed. Here's an example. This system has a design flow rate of 14,000 CFM at 2 inches of water. So we need a 10 horsepower motor operating at 710 RPM. At part load, the VAV boxes close and less airflow is needed. This allows the system to unload along a system modulation curve. This curve terminates at the duct static pressure set point, in this case, 0.65 inches of water. At a part load condition, A, only 9,500 CFM is needed to offset the load, so the fan motor speed can be adjusted downward. This part load point A falls along the system modulation curve, but at lower RPM and static pressure. 540 RPM, and 1.3 inches of water. And consequently, the fan motor draws less power, 4.1 horsepower. So, for a 32% reduction in airflow, we get 59% in energy savings. Okay, let's take a closer look at the VAV boxes, which are available in different styles. The most basic style is a cooling-only box with a motorized damper. Here, conditioned primary air from the central unit enters the box. The damper modulates to create an air resistance and limit the amount of conditioned air flowing into the zone. VAV boxes may be equipped with heat. This is usually an electric heater or a hot water coil. VAV boxes may also be equipped with an airflow measuring device, such as this flow ring, to measure the airflow passing through the box. There are several other variations in the market too. The series and parallel fan-powered VAV box draws air in from the plenum and uses a small terminal fan to deliver conditioned air into the zone. And there's another variation called dual duct, where two streams of air, one warm and another cool, flow into the VAV box to make sure the right supply air temperature is produced for each zone. Today, we'll focus only on single duct VAV boxes. Now, I've mentioned heating a few times, so let's explore this. When heating, the VAV box damper may be at its minimum position to ensure adequate ventilation and recirculated air. There are a variety of ways these systems can provide heat, ranging from baseboard heating to varying types of diffusers. Next, let's look at system operation. VAV systems can operate in several different modes, depending upon the time of day and zone needs. This is often dictated by a schedule programmed into the controller. In the occupied mode, the system maintains the desired set point temperatures in each zone. Some zones might need cooling and others heating. The central unit uses its heating and cooling to maintain a discharge air temperature set point, like 55 degrees. The central unit also modulates the supply fan speed to maintain the duct static pressure set point. The outer air damper modulates to satisfy the ventilation requirement. The return or relief fan is modulated to maintain the indoor to outdoor static pressure differential set point. VAV terminals vary supply airflow to maintain zone temperature at the occupied heating or occupied cooling set point, such as 70 or 75 degrees respectively. If the zone temperature is above 75, the damper modulates to let more cool supply air in. And if the zone temperature is below 70, the damper is at its minimum and reheat may be used. Now, in the unoccupied mode, the system allows the zone temperature to drift, cooler or warmer from the occupied set points. This allows the system to shut off and save energy. Sometimes this is called night setback. And because there are no people, there's no need for ventilation, so that damper is closed. Now, the latest version of ASHRAE's ventilation and indoor air quality standard, Standard 62.1, requires that space dew point temperatures not exceed 60 degrees Fahrenheit in some cases. So, during unoccupied mode, the system may still monitor temperature and humidity to ensure that these limits are not exceeded. To get back to occupied set points, prior to occupancy, the system may start up before people arrive. Morning warm-up or morning cool-down modes are used for this purpose. The system will attempt to heat or cool as quickly as possible. Now here's a morning warm-up scenario. The heaters in the VAV boxes may be used, or like in this example, the central unit's modulating heater is on. The outer air damper is closed. No ventilation is needed because the zones are still unoccupied. With a modulating heater, the supply fan operates to maintain the duct static pressure set point. If there's a return fan, it may be on, but relief fan operation is not needed. When zones reach their set point, the VAV dampers will close. VAV systems can also use airside economizing. This energy-saving control strategy uses outdoor air as a source of free cooling when the ambient temperature allows. This system has a discharge air temperature set point of 55 degrees. When the outdoor air temperature is colder than this, modulated economizer, shown in yellow, is used. This means the outdoor air and return air dampers are modulated to achieve the discharge air temperature set point. When the outdoor temperature climbs above the discharge air temperature set point, the system may use both outdoor air and mechanical cooling for integrated economizing. Here, the outdoor air damper is wide open and mechanical cooling supplements as needed. And when the outdoor air temperature rises above the high limit shutoff condition, it no longer makes sense to economize because of the cooling energy needed. At this point, the system resumes normal cooling operation. There are many high limit shutoff control strategies, including dry bulb temperature control, or like in this example, dry bulb and enthalpy control.
Next, the team is going to discuss how to optimize a new or existing VAV system to reduce energy usage, emissions, and operating costs. And that usually starts with controls.
To fully leverage the advantages that we will discuss in this section, it is advisable to implement a building automation system, or BAS. Modern BAS systems are both robust and interoperable. These systems can come with prepackaged control algorithms, streamlining their deployment and reducing costs. Additionally, a building automation system ensures continuous optimization of the building, enhancing comfort and energy efficiency. ASHRAE Guideline 36 outlines high-performance sequences of operation for HVAC. It aims to standardize control sequences to ensure optimal efficiency and performance. By utilizing these proven sequences, engineering time is significantly reduced. This also minimizes the programming and commissioning time required by contractors. The goal is substantial reduction in energy consumption, operational costs, and system downtime. The guideline promotes resilient systems by including automatic fault detection and diagnostics to provide continuous monitoring and troubleshooting. Modern control for optimizing multiple zone VAV systems can follow Guideline 36 to apply several optimization strategies. Now, I am going to discuss a strategy for controlling VAV boxes, which is called dual maximums or dual max VAV. When the zone requires cooling, the VAV damper modulates between the maximum airflow of 100% and the minimum of 20% to maintain zone temperature at its cooling set point, while the reheat coil is off. When the cooling load has decreased to the point where the VAV damper has reached the minimum airflow, the zone temperature is allowed to drift downward through the deadband between the cooling and heating set points, while the airflow is maintained at minimum. If the zone temperature drops below the heating set point, the reheat coil is modulated to maintain constant discharge air temperature. As the heating load increases, the discharge temperature is reset upwards while the airflow is kept at minimum. When the discharge air temperature reaches its designed heating set point, which is 90 degrees in our example, the VAV damper begins to modulate further open, increasing the airflow delivered to the zone, while the reheat coil is modulated to maintain discharge air temperature at this design. And dual max requires the use of modulating gas heat, or SCR electric heat. Next, Greg will review optimization strategies regarding system startup.
First, let's start with how a building traditionally works to prepare the space for the occupants. During hours when the building is expected to be unoccupied, the HVAC system is typically shut off and zone temperature is allowed to drift away from its occupied set point, often called night setback. The green shaded region indicates the scheduled occupancy period between 7 a.m. and 6 p.m. The system shuts off at 6 p.m. And because it's cold outside, the zone temperature cools down overnight. The time at which the system starts back up again is usually scheduled early enough so that the zone temperature reaches its occupied set point prior to 7 a.m. on the coldest or warmest morning of the year. But as a result, on all other days, the system starts earlier than it needs to. The system is scheduled to start up at 5 a.m. When the system turns on, it takes just under an hour for the zone to warm back up to its occupied heating set point of 70 degrees Fahrenheit. Now it remains on and continues heating the building for the 70 minutes remaining until scheduled occupancy, thus wasting energy. The system goes into unoccupied or night setback at 6 p.m. As you can see, the system operates at set point prior to the scheduled occupancy time and all the way through the day until the program occupied period has expired. A more efficient approach is the strategy called optimal start or morning warm-up. Rather than starting back up at the same time every day, this strategy determines the length of time required to bring a zone from its current temperature back to its occupied set point. The system waits as long as possible before starting up. This allows the zone to reach its occupied set point just in time for scheduled occupancy. This strategy saves energy by not heating the building too early. The optimal starting time is determined by using the difference between the actual zone temperature and the occupied set point and comparing this difference with the historical performance of how quickly the zone has been able to warm up. A similar strategy is optimal stop. As I mentioned at the end of the occupied period, the system shuts off and the temperature is allowed to drift away from its occupied set point. However, in many cases, the building occupants might not mind if the zone temperature drifts just a few degrees before they leave for the day. Optimal stop determines how early the heating or cooling can be shut off, such that the temperature in the zone will not drift more than 2 degrees from the occupied set point by the end of the scheduled occupancy, which is 2 degrees below the occupied heating set point, as shown, or 2 degrees above the occupied cooling set point. The supply fan continues to operate and the outdoor air damper remains open to continue ventilating the building. Only cooling and heating are shut off. This strategy further saves energy by allowing indoor temperatures to begin drifting early. Both optimal start and stop strategies can be used for cooling and heating. During the unoccupied mode, the indoor temperature can sometimes drift up, which is warmer than the occupied cooling set point. This requires the system to enter a morning cool down mode prior to occupancy. However, if the outdoor air dry bulb temperature is cooler than the indoor temperature during these unoccupied hours, it is possible to use the outdoor air for free pre-cooling. This strategy, often called unoccupied economizing or night purge, can save energy by pre-cooling the building prior to the morning cool down period. Unoccupied economizing uses the BAS to determine if the condition of the outdoor air is suitable for free cooling, which is allowed if the outdoor air dry bulb temperature is 15 degrees cooler than the current zone temperature. In addition, an outdoor air humidity or enthalpy sensor can be added to prevent unoccupied economizing when the outdoor air is cool but humid. I'm now going to pass it over to Mayra to talk about fan pressure optimization.
As Eric mentioned earlier, in a multiple zone VAV system, as the cooling loads in the zone change, the dampers inside the VAV boxes modulate to vary airflow supply to those zones. This causes the pressure inside the supply ductwork to change. The supply fan needs to modulate to maintain a certain static pressure in the ductwork. Historically, the system has maintained a constant static pressure set point to provide adequate supply airflow for every zone. But it is possible to optimize the static pressure control function to provide just enough pressure in the duct to satisfy the most wide open box. Reducing fan pressure reduces fan energy consumption, but it requires communicating controllers on the VAV boxes to do it. Each VAV box controller knows the current position of its damper. The VAS continually polls these individual box controllers, looking for the zone with the most open damper. The fan's static pressure set point can be reset lower and lower until this particular VAV damper is nearly wide open. During this process, total supply airflow remains constant because the damper in each zone opens to maintain its required airflow. But the static pressure in the supply duct is reduced. Same airflow, just less pressure. The supply fan generates only enough static pressure to push the required quantity of air through this critical VAV box. Previously, Eric showed an example of the variable speed operation in a traditional VAV system with fixed static pressure setpoint control. The part load point was at 9,500 CFM. Now let's look at it with fan pressure optimization. By modulating the duct static pressure setpoint, a new VAV system modulation curve is created here, depicted in green. Now, the same 9,500 CFM on part load create point B when it reaches the optimized curve, reducing the static pressure to 1 inch of water and the fan motor power of 3.4 horsepower at 500 RPM. Of course, less static pressure, less RPM, and less fan motor power means less energy. The area between these two curves represents the energy savings at part load. Fan pressure optimization has several benefits. First is that it reduces supply fan energy use. At part load airflows, the supply fan operates at a lower static pressure and uses less energy than if controlled to a constant duct static pressure setpoint. Second, because the supply fan doesn't need to generate as much pressure, it typically generates less noise. And with lower pressures in the ductwork, the damper in the VAV boxes will be more open, resulting in less noise generated at the boxes. A third benefit is the reduced risk of fan surge. By allowing the fan to operate at lower pressures when delivering reduced airflows, the fan operating point is kept further away from the surge region. A fourth benefit is that by operating at lower static pressures, less air leaks out of the duct system, avoiding further energy waste. And finally, fan pressure optimization allows flexibility when locating the duct static pressure sensor. Because the system controller uses the position of the VAV dampers to reset the static pressure setpoint, the sensor can be located almost anywhere in the supply ductwork. The most convenient location is usually near the outlet of the air handler or rooftop unit. In some cases, the sensor can be factory installed and tested and not relocated in the field. But it is usually better to mount it a few duct diameters away from the fan discharge, where turbulence is lower and static pressure is higher. When located near the fan outlet, the same sensor can also serve as a high pressure limit to help protect the ductwork from damage in the event of a fire damper closing. One drawback is that VAV boxes need to be pressure independent with unit controller. For new systems, this is the standard, but for a retrofit, it could be an issue. Fan pressure optimization can be programmed into a building automation system. It can also be implemented using the trim and response sequences of operation. As I mentioned before, ASHRAE Guideline 36 aims to provide uniform sequences of operation for HVAC systems to maximize energy efficiency, performance, and control stability. The guideline includes the trim and response setpoint reset logic, which resets any setpoint in a system with downstream devices. This logic is particularly effective for controlling a single variable influenced by multiple zones, such as the static pressure setpoint in a VAV air handler. It is simpler to tune than traditional control loops and offers rapid responses without high-frequency disruptions, balancing energy consumption with comfort. Let's explore how trim and respond functions. This logic adjusts setpoints for variables like pressure or temperature in HVAC systems. For instance, in a fan pressure application, it continuously lowers or trims the static pressure setpoint until a downstream zone is no longer satisfied and requests an increase. When enough requests meet a specified threshold, the setpoint is raised. This is the respond part. If the number of requests fall below the threshold, the setpoint resumes its gradual reduction or trimming. The number of requests each member sends depend on predefined rules set up in the logic. Now let's look at an example. The following example shows how trim and respond operates to perform fan pressure optimization. We start with an initial duct static pressure setpoint In this example, 1 inch of water. We will define for the system some parameters. We will continuously trim at 0.04 inches and will respond a little faster at 0.06 inches. We set a maximum value for the duct static pressure set point of 2 and a minimum of 0.7 inches. Next, we define the rules. Each VAV box controller will generate requests if any of the following conditions are true. If the VAV damper is less than 95% open, the controller sends 0 requests. If the VAV damper is more than 95% open, it sends 1 request until the damper is less than 85% open. If the VAV damper is more than 95% open for longer than 1 minute, and the measured airflow is less than 70% of its current airflow set point, it sends 2 requests. If the VAV damper is more than 95% open for longer than 1 minute, and the measured airflow is less than 50% of its current airflow set point, it sends 3 requests. The system level controller will trim or reduce constantly the duct static pressure set point until the sum of all the VAV box's requests reach a threshold of 2 requests. After 2 requests, the system will respond, increasing the duct static pressure set point in increments of 0.06 inches until there are 2 or fewer requests. It might be easier to see a graph of the operation. The x-axis shows the time increments of the building operation in minutes. On the left y-axis is the duct static pressure set point in inches of water, which will be depicted in the black dotted line. We are plotting on the same graph the sum of requests from the VAV boxes on the right y-axis, depicted as blue columns. Remember, the threshold is 2 requests, here represented in a horizontal red line. We have determined that the initial duct static pressure set point is 1 inch, and there is a time delay before we start to count the requests. The static pressure set point starts to trim or decrease, and we see some requests appear in the system, but still under the threshold, so the system continues to trim. Remember, trim and respond is intended to maximize energy efficiency and performance. What happens when the sum of requests is above the threshold of 2 requests? Well, the system responds to the number of requests by increasing the duct static pressure set point. Now, all VAV boxes are satisfied, and there are no more requests. Therefore, the system starts trimming again until the sum of the requests exceeds 2, where it will respond again, increasing the set point. This trimming and responding will continue all day long, which is how the fan static pressure is optimized. If you want to step through this example deeper, see the Engineer Newsletter Live System Controls for Applying ASHRAE Guideline 36 listed in the references at the end. There are other optimization strategies. Eric will explain discharge air temperature reset.
The next strategy we'll discuss is discharge air temperature reset, sometimes called supply air temperature reset. The goal is to raise the discharge set point to reduce compressor and reheat energy use. When the set point is increased from 55 to 60 degrees, the compressors can unload, cycle, and don't have to work as hard, which reduces energy use. Additionally, a warmer discharge set point increases the possible number of airside economizing hours. But there are trade-offs. First, zones that require cooling will need more air to offset the load, which increases fan energy. Next, a warmer discharge temperature means the cooling coil will perform less dehumidification, and this could result in higher humidity in the occupied zones. The typical goal is to first reduce the supply airflow and achieve energy savings from reduced fan speed. Then, raise the discharge set point to reduce reheat energy use and increase the economizing potential. And this could be done while monitoring zone humidity to ensure comfort is maintained. The classic implementation uses outer air temperature and VAV damper position to determine what to do. Using outer air temperature, the system establishes the discharge air temperature set point. So when it's cool outside, the BAS resets the set point upward to 60 degrees. And when it's warm outside, the discharge air temperature is at its normal set point, 55 degrees. And for conditions in between, a linear function is used. If there's a zone with a large cooling load, this warmer air might not be cold enough to offset the entirety of the load. Using the zone temperature and VAV damper position, the controls can determine that the reset is too much and simply lower the set point a degree or two to see if that solves the problem, or revert back to 55 degrees. Another option is to size zones with expected high cooling loads using the reset supply air temperature. Said another way, size the airflow based upon 60 degrees rather than 55 degrees. Now with this strategy, it might make sense to discontinue reset if space humidity climbs beyond an acceptable level. One method is to install relative humidity sensors in zones where this is expected to occur. When relative humidity exceeds a program threshold, such as 60%, or the space dew point temperature exceeds 60 degrees, the discharge reset can be adjusted or discontinued. Monitoring the outdoor ambient dew point temperature could also be used to determine when to discontinue discharge air temperature reset. For example, when the outdoor dew point temperature exceeds 60 degrees, stop or adjust the reset. Another implementation uses trim and respond from Guideline 36. This is the same control strategy that Mayra demonstrated with fan pressure optimization. In that case, we were trimming downward by reducing the fan static pressure set point. Here, we're trimming upward. In this example, zone temperature is compared to the zone set point. The number of requests sent is proportional to the difference between the zone temperature and its set point. So if temperature control is lost, more requests will be sent. Here's an example. After a 10-minute delay, requests start coming in, but they're below the ignore threshold. So the discharge air temperature set point slowly goes up. Once the requests exceed the threshold, the set point is decreased until the requests subside. And this polling and calculation continues throughout operation, with a goal of increasing the discharge air temperature while maintaining comfort. Okay, let's shift gears and talk about ventilation. ASHRAE Standard 62.1 allows reduced ventilation based upon changing conditions, like varying occupancy. So, the system can respond to real-time conditions rather than simply operating at design ventilation. There are two approaches available with multiple zone VAV systems: demand-controlled ventilation at the zone level and ventilation reset at the system level. First, demand-controlled ventilation. The system can be equipped with different means to determine or measure individual zone population. Common examples include time of day schedules programmed into the VAS, which are best used for zones that have predictable population patterns. Occupancy sensors for low-density private offices or densely occupied zones with minimal population variation. And carbon dioxide sensors, which measure CO2 concentration in densely occupied zones with highly variable populations. This gives designers the flexibility to select the right sensor for the right application. And you can even connect to a third-party system that monitors population, like those found in retail or ticket sales. Now, with the current occupancy levels determined, the system can calculate the required breathing zone outdoor airflow rate for each zone. Remember, the VAV box flow ring continuously measures primary airflow being delivered to the zone, so the VAV controller can calculate the real-time outdoor air fraction. Next, the standard 62.1 system calculations can be computed to identify the system ventilation needed. This is the system-level calculation commonly called ventilation reset. The system-level controller periodically gathers data from all the VAV controllers and solves the equations with the current system ventilation efficiency to determine how much outdoor air must be brought in to satisfy the current requirements. Then, the system-level controller sends this calculated outdoor airflow set point to the central unit, which modulates a flow-measuring outdoor air damper to maintain this new airflow set point. This approach results in the right amount of outdoor air delivered to the worst-case zone and minimizes excess ventilation in the other zones. There are some advantages and possible drawbacks. This strategy has a significant potential to save energy, and the ventilation reset calculations can be performed without additional sensors. Now let's look at the possible drawbacks. First, for demand-controlled ventilation, communicating controls are required to send VAV box and airflow information to the system controller. And a building automation system is needed to perform the calculations and coordinate terminal and system operation. And finally, an outdoor airflow measuring system is needed at the central unit. The building automation system typically uses a time of day schedule to define when a zone is occupied or unoccupied. When an occupancy sensor is used in combination with this, the sensor can determine whether the zone is actually occupied. This can be used to enable occupied standby mode. When the zone is scheduled to be occupied, but it's not, the system can shut off the lights, adjust the zone temperature set point by a degree or two, and reduce the minimum required outdoor airflow. Standard 62.1's ventilation rate procedure includes a people and area-based component. When there are no people, the system can ventilate for only the area-based component. So for example, consider a 1,000 square foot meeting room with a design occupancy of 50 people. When the meeting room is occupied, the zone requires 310 CFM of ventilation air. During occupied standby, when no people are in the space, the zone can be ventilated at just 60 CFM, the area-based component only. In fact, Standard 62 permits some zone types to be reset to zero ventilation, provided normal ventilation can be resumed immediately when occupancy is detected. So, if properly equipped and controlled, this zone could receive zero ventilation when in occupied standby mode. And finally, the VAV minimum could be reset downward to reduce or eliminate the need for zone reheat. Each of these actions is designed to save energy. Now, we've been talking a lot about Guideline 36. Many of the optimizations discussed are covered within the guideline. This includes optimal start, fan pressure optimization, discharge air temperature reset, and even the ventilation strategies. And while Guideline 36 covers high performance control sequences, many of these optimizations are also found in ASHRAE Standard 90.1, which is typically the bare minimum.
I'm going to discuss the design opportunity to lower the supply air temperature delivered to the VAV boxes. For example, what if we supply it 48 degrees versus the commonly used 55 degrees? Supplying air at a colder temperature allows the system to deliver a lower airflow rate. This can significantly reduce fan energy use, and it can also allow fans, air handlers, and VAV boxes to be downsized, which reduces installed costs. Sometimes ductwork is also downsized, which further reduces installed costs. Another advantage is that delivering colder air means that the air is drier, which can lower indoor humidity levels. However, while supplying air at a colder temperature reduces fan energy use, it can increase reheat energy and result in fewer hours when the airside economizer can provide the necessary cooling. These impacts partially offset the fan energy savings. Another potential drawback is duct condensation. However, all systems should have properly insulated and sealed ductwork. If proper attention is not paid to this, condensation can occur even in a 55-degree system. Let's look at the reheat issue a bit deeper. Here's a VAV box used in a conventional 55-degree supply air system. Design primary airflow for the zone is 1,000 CFM, and the minimum primary airflow setting is 200 CFM, or 20% of design. As the sensible cooling load in the zone decreases, the damper in this VAV box modulates to reduce primary airflow delivered to the zone. When primary airflow reaches the minimum setting, while the air handling unit is in the cooling mode, the heating coil warms the air to avoid overcooling the zone. For this example, the reheat coil would be activated when the space-sensible cooling load drops below 20% of design. Now let's look at the same zone, but for a cold air, 48-degree system. Design primary airflow is reduced to 740 CFM. The minimum primary airflow setting in terms of CFM is unchanged. It is still 200 CFM. This is because the minimum setting ensures proper ventilation and proper operation of the supplier diffusers. While the minimum CFM is the same, the percentage is higher, 27% rather than 20%. What this means is that the reheat coil would be activated when the space-sensible cooling load drops below 27% of design, which means that it will activate sooner than in a conventional 55-degree supply air system. But if you use discharge air temperature reset to raise the supply air from 48 back up to 55 degrees during mild weather, this difference gets a lot smaller and maybe even goes away. Therefore, optimized system control is crucial to fully realize the potential energy savings of a lower temperature VAV system.
Next, we're going to transition to a subject gaining popularity, electrification. Many owners and designers are looking to replace fossil fuel heating with electrified heating to reduce overall emissions.
We can electrify a VAV box by utilizing an SCR electric heater or a hot water coil from a heat pump chiller. In this example, we are utilizing a hot water coil. This is a single duct VAV box with 325 CFM of airflow at 60 degrees. The designer has specified a 90-degree supply air temperature, which results in a 30-degree temperature rise across the heating coil. Using the sensible heat equation, this results in the need to size the hot water heating coil for 10,600 BTUs per hour. A potential means to reduce the temperature of the hot water is to incorporate a heat pump chiller or heat pump delivering 105-degree hot water, for instance. Lower temperature hot water tends to reduce lift on the chiller, thus reducing energy use. Although there are many advantages of heating with lower temperature hot water, there are a few factors that should be considered. VAV boxes typically have fewer heating coil options available to choose from or configure. Now let's look at this example in more detail and apply lower temperature hot water to the coil. In this example, either a 3 or 4 row coil is needed to provide the required heating capacity of 10,600 BTUs per hour. In some cases, you can upsize the VAV box from an 8-inch to a 10-inch box as a method to further minimize the impact of both pumping and supply fan energy use. However, in some cases, upsizing the VAV box inlet diameter may require using a higher minimum airflow setting to ensure proper control at lower airflows. It is recommended that the dual max VAV control sequence be implemented to allow for less hot supply air temperatures when heating is required. Another strategy for electrification is to use fan-powered VAV boxes. As Eric mentioned earlier, VAV boxes are a key component in any multiple zone VAV system. Fan-powered VAV boxes can take advantage of the available plenum heat. They come in 2 main configurations, parallel and series. Each configuration has its own advantages and disadvantages. I'm going to discuss the main difference and a few pros and cons of using a parallel versus a series fan-powered VAV box. First, let's discuss series fan-powered VAV boxes and start with the pros, where the fan operates continuously, thus providing consistent air circulation, which often enables better temperature control, stable comfort levels, and air distribution. However, there are a few potential cons to consider when designing a series VAV system. Continuous fan operation leads to higher energy consumption. Also, fan operation can result in higher noise levels in the space and can lead to more wear and tear on the fan and increased maintenance requirements. I will now discuss the pros and cons of parallel fan-powered VAV boxes. These tend to be more energy efficient due to the fan only operating when additional heating is needed. There is generally less noise compared to the series VAV box since the fan runs intermittently based on heating demand, and there are fewer moving parts operating continuously. Thus, maintenance can be simpler and less frequent. As for the cons, temperature control can be less precise, especially in spaces with varying occupancy or higher heating loads. Comfort levels during periods when the fan is off can lead to less air circulation, potentially leading to discomfort in some zones. Reduced air circulation when the fan is off can lead to lower indoor air quality versus series VAV boxes. The choice between parallel and series VAV boxes based on plenum heat depends on the specific requirements of the building, including energy efficiency goals, budget constraints, and the desired level of comfort and air quality. Additionally, the effectiveness of plenum heat distribution should be considered, especially in large or more complex spaces. The designer should also consider available plenum heat with buildings using LED lighting rather than fluorescent or incandescent lights. Now let's discuss electrifying the rooftop or air handler. Electrifying a VAV system can be done in several different ways. First, let's look at the central unit, then the terminals. A central unit may include a heating coil to temper the supply air when it's cold outside. Supply air tempering is performed to raise the discharge air temperature to a set point like 55 or 60 degrees and prevent cold air from flowing through the duct system. A gas heater could be replaced with an electric resistance heater or a hydronic or steam coil. If it's a DX rooftop, it could also be a heat pump. Hot water can be provided from an electrified boiler, chiller heat recovery, or a heat pump. With a boiler, we could supply water at 180 degrees, but electrified heating is more efficient at lower hot water temperatures. Let's consider a unit with a hydronic heating coil. This unit has 2,000 CFM of 10-degree outdoor air mixing with 2,000 CFM of 70-degree recirculated air. The resulting mixed air temperature is 40 degrees, which is below the desired discharge air temperature set point of 60 degrees. So this unit will operate in supply air tempering mode. The question becomes, can we provide a hydronic heating coil with a lower heating water supply temperature? Here's the original single roll coil selected at 180 degrees and 80 fins per foot to make 86,800 BTUs per hour. Heated water flows at 1.65 GPM. The coil has a fluid pressure drop of 0.15 feet of water and an airside pressure drop of 0.017 inches of water at the design heating condition. With a 104 degrees supply water temperature and the same fin density, the fluid flow rate must go up. The fluid pressure drop also goes up, but the airside pressure drop remains the same. The next option reduces the supply water temperature to 105 degrees. In this region, heating equipment typically has better efficiency and more capacity. The coil still achieves the same heating output with the same fin density, but the fluid flow rate is dramatically higher. The fluid pressure drop is also much higher. Again, the airside pressure drop remains the same. So how can we use 105-degree water without sacrificing fluid pressure drop? The last selection increases the fin density to 120 fins per foot. The fluid flow rate, fluid pressure drop, and airside pressure all increase, but not as much as before. So this heating coil could be replaced and we could achieve the same heating performance all with a single roll coil. Providing the same capacity with a lower hot water supply temperature does require a higher fluid flow rate, which will affect pump, pipe, and valve sizing, and it increases pumping energy. Air-to-air energy recovery could be used to preheat the ventilation air as well. In this case, heat is transferred by a rotary heat exchanger from the exhaust to the outdoor airstream. So the resulting supply air temperature is 60 degrees without the use of a heating coil. But in cold climates, preheat may be required for frost control. We recently had a program on state-of-the-art air-to-air energy recovery, and I'll leave that in the bibliography. Next, I am going to discuss how to electrify with a unitary heat pump. Historically, heat pump rooftop units have been available in smaller size ranges, up to about 25 tons, but many manufacturers are now developing larger sizes. Here is a heat pump rooftop unit applied with VAV boxes that include electric heat. Rather than changing over to supply warm air during the winter, this rooftop unit continuously supplies cool air year-round, while zone heat is provided by the VAV boxes. During morning warm-up mode, the rooftop can use the heat pump to warm the building prior to occupancy after a cold night or weekend. In a cold climate, during normal operation, the mixture of recirculated and outdoor air might be too cold to deliver down the duct to the VAV boxes. If this is the case, the rooftop unit might use an SCR electric heater to temper this cold mixed air up to the supply air set point, say 60 degrees, or in the case of a dual fuel heat pump, a modulating gas heater could be used for this. We discussed unitary heat pumps in greater detail during the 2024 E&L titled Modern Unitary Heat Pump Applications. It's listed in the bibliography.
Like everything else, technology has also improved VAV systems. Mayra will provide some examples of technological advances in VAV systems.
One example is related to systems using newer A2L refrigerants. Equipment controllers can now start safety mitigation actions in real time if a refrigerant leak is detected. Another example is real-time connectivity, or the Internet of Things. This enables connectivity of the VAV system components through the Internet to enhance their functionality. Open and secure protocols, as well as application programming interfaces, or APIs, allow different vendors to integrate devices and web services. Indoor and outdoor sensors allow for real-time monitoring of temperature, humidity, static pressure, indoor CO2, and particulate matter. For example, connecting the VAS to a weather forecast site can provide air quality due to wildfires that would alert the system to reduce ventilation until the outdoor conditions improve. Or connecting to a nearby weather station could fetch real-time outdoor temperature and humidity without the need of local sensors that need to be calibrated on site. Next, building management systems are comprehensive automation systems designed to control and monitor mechanical and electrical equipment across multiple buildings, synchronizing HVAC operation with lighting or security, all accessible from a single sign-on or any mobile device. With new technologies and the use of the cloud, storage is no longer a limitation. We can now monitor the performance of systems in our buildings with more data and keep records for extended periods. Having this data available simplifies the use of analytic tools to troubleshoot and identify potential issues or opportunities to conserve energy and lower operational expenses, all while maintaining a comfortable indoor environment. For example, using a graphic of the energy use of a year, it is possible to visually identify energy peaks in the building that could point at some VAV system schedule that needs to be adjusted with optimal start. Remote connectivity also enables digital servicing and predictive maintenance. Unlike traditional equipment servicing, where a technician checks the equipment condition only during quarterly visits, digital servicing allows for 24/7 monitoring. By tracking key variables in the VAV equipment and systems, potential issues can be detected early. This allows the maintenance team to address problems before they escalate, preventing major issues or operational downtime due to damaged equipment. Here is an example of a digital service inspection. On this service technician tool, We can see the digital inspection for a rooftop unit for the last 3 months. We can see the categories of analytics concerning to the unit, like the unit controls, sensors available in the equipment, evaporator, condenser, and so on. Each category has specific tests. For example, the first test here is for supply fan off during occupied. This means that during an occupied time, the supply fan was off in several instances. We can see that 62 of 90 tests failed during the last 3 months. On the right side, we can see that sometime early June, the test started continuously passing. In this case, the service technician had identified this issue digitally and was able to make some changes to the system remotely to make sure that the supply fan is on during occupied times. We can't talk about technological advancements for VAV systems without mentioning the use of artificial intelligence, or AI, as a tool for simplifying some of these tasks. It can be used for optimization of the same variables that we have mentioned before. Continuous commissioning is crucial. Over time, overrides to the VAV system or changes in layout can lead to inefficient building operations. AI can help optimize these operations by implementing improvements that weren't originally programmed into the building automation system. Additionally, artificial intelligence enhances data analytics, allowing us to detect anomalies and patterns that could indicate potential issues. VAV systems continue to evolve with new technologies, demonstrating their resilience and robustness.
We have talked about all these optimization strategies for VAV systems, but do we know how much better they make our buildings? Next, Mayra will show us a case study.
Let's look at this 30,000 square feet office building in Kansas City with 2 VAV rooftop units, each with a dozen VAV boxes. In 2019, the occupant reported high demand peaks during winter mornings. Reducing demand was the customer's priority since they had demand and ratchet demand charges. The equipment started every day at 4 a.m. to have the building ready by the time occupants would arrive. Fan pressure optimization had been programmed originally. The VAV systems had a constant discharge temperature of 55 degrees, and spaces were overventilated. The optimization strategies that we've been describing were implemented in their system controller. Let's look at the results after these optimization strategies were applied. This graphic is sourced from the BAS of the building. On the x-axis, we have timeline spanning from April 2019 to 2025. The y-axis represents the energy use intensity, measured in kBTU per square feet per year, depicted by the blue line. Additionally, the cost use intensity is shown in the red line. In April 2019, the energy use was approximately 70 kBTU per square feet per year, with a target to reduce it 24%, aiming for 53 kBTU. In May 2019, several optimization strategies were implemented in the building, including optimal start, discharger temperature reset, and the existing fan pressure optimization was fine-tuned. Following these optimizations, energy use significantly decreased, reaching 55 kBTU by the first quarter of 2020, a 21% reduction in less than a year, nearly achieving the target. When COVID-19 hit and stay-at-home orders were issued, energy usage dropped to around 47. As people began returning to the office towards the end of the pandemic, energy use started to rise again. To protect building occupants, ventilation rates were significantly increased during this time. By the end of 2021, demand control ventilation was implemented and ventilation rates were adjusted back to standard 62.1 rates. This optimization further reduced energy usage to the high 40s. The building started with 70 kBTU, and by now we have surpassed our original reduction goal. The building transitioned to a hybrid model, with employees at the office at least 3 days a week. In December 2023, a rate structure change occurred, and artificial intelligence was later introduced in 2024, as the building operators continue looking to reduce energy use and cost. You can see that by the end of the graph, The energy cost increased because of recent winter weather extremes, which reset the yearly peak and ratchet charges. By implementing these optimization strategies in the VAV systems, the building achieved a 31% reduction in energy use and a 23% decrease in energy cost intensity.
Great example to close with. Thanks, guys. As you just heard, optimizing multiple zone VAV systems offers many benefits in terms of energy savings, operational efficiency, and enhanced comfort for building occupants. By implementing strategies such as fan pressure optimization, discharge air temperature reset, and demand-controlled ventilation, buildings can achieve reductions in energy consumption, operational costs, and emissions. The integration of advanced technologies further enhances system capabilities, enabling real-time monitoring, predictive maintenance, and continuous commissioning. As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic. Or contact your local Trane account manager for specific information on Trane systems, equipment, controls, and services. For those of you seeking continuing education credit, check out the newest online courses in the Trane Education Center. And for those of you viewing in person, please ask your local host about details for upcoming Engineers Newsletter Live programs, or check them out at trane.com/ENL. And we launched a new podcast last year, hosted by our very own Dan Gentry and Charlie Jellin. So please check out Cool Air Hot Takes on your favorite platform and subscribe. Finally, for those of you viewing in person, please fill out a survey and let us know what you thought of today's program. Thanks for joining us today. We look forward to seeing you next time.